Black holes, they're pretty much the universe's ultimate mystery boxes, right? These are objects so extreme they push our understanding of reality to its absolute limit. But what are they really? And how in the world did we even come up with such a wild idea? All right, let's get into it and unpack the story of one of the most fascinating concepts in all of science.
You know, what's truly amazing about this question is when it was first asked. It sounds like something right out of modern physics, but it was actually posed way back in 1783 by a guy named John Michell. This was over a century before Einstein, just using Newton's basic laws of gravity. He imagined these dark stars that would be invisible simply because their gravity was too strong for even light to escape. The seed of the idea was there, but the physics just wasn't ready to handle it yet.
So in this explainer, here's our game plan. We're going to trace that idea through 5 key chapters. We'll kick things off with those early concepts, then see how Einstein's theories kind of stumbled upon their existence. After that, we'll define their key parts, understand how they're actually born, and finish with a completely mind-bending quantum twist from the one and only Stephen Hawking.
So first up, an idea before its time. This is where the story begins, back with classical physics and a pretty simple understanding of gravity as just a pulling force.
So after Mitchell and later a scientist named Laplace played around with this concept, the whole idea of a dark star just kind of went dormant for over 100 years. The problem was Newtonian gravity just wasn't the right tool for the job. To truly understand these things, we needed a completely new way of thinking about the universe itself. And that finally came in 1915.
Let's move on to our second chapter and see how this all builds, Einstein's reluctant prediction. This is where everything, and I mean everything, changes. Because Einstein didn't just update the laws of gravity, he completely rewrote the entire rulebook.
See, Newton saw gravity as this invisible rope pulling things together. But Einstein's theory of general relativity, whoa, it revealed something so much deeper. He basically said there is no force of gravity. Instead, what's happening is that mass and energy literally bend and warp the very fabric of spacetime. What we feel as gravity is just us moving through that curved landscape.
And get this, just months after Einstein published his theory, a soldier on the front lines of World War I named Carl Schwarzschild found the very first exact solution to these incredibly complex equations. He was just trying to calculate the shape of spacetime around a single simple sphere of mass.
And his solution was, well, it was bizarre. The math predicted a central point of infinite density, a singularity, and a boundary around it from which nothing could ever escape. And this is so important. This wasn't just speculation anymore. It was a direct mathematical prediction of general relativity. But the idea was so strange that even Einstein himself rejected it. He believed that in the real world, nature would somehow prevent these crazy objects from ever forming. But the idea just wouldn't go away. So, for our third section, let's dissect this theoretical beast and take a look at the anatomy of a black hole.
The most famous feature, of course, is the event horizon. Now, this isn't a physical surface you could touch. Think of it more like the edge of a cosmic waterfall. Once you cross it, the curvature of spacetime is so extreme that every possible path forward leads only one way, toward the center. There is absolutely no going back.
And at that center is the singularity. This is where our current laws of physics just completely fall apart. All the mass that has ever fallen into the black hole is crushed into a point with zero volume and infinite density. We can't see it, of course, because it's forever hidden behind that one-way door of the event horizon. For decades, these objects had these really clunky technical names. But in the 1960s, the physicist John Archibald Wheeler finally gave them the simple, evocative, and slightly terrifying name they deserved: black holes.
So the theory is there, the anatomy is defined, and now it has a fittingly dramatic name. But how does the universe actually create one? Let's dive into Section 4, the birth of a monster.
Well, the most common way to make a black hole is through the death of a truly massive star. Throughout its life, the star is in this constant battle, the outward push from nuclear fusion versus the inward crush of its own gravity. When the star runs out of fuel, fusion just stops, and gravity wins. In a fraction of a second, the core collapses, triggering a massive supernova explosion. But what happens to the core that's left behind depends entirely on its mass. This number, about 1.44 times the mass of our Sun, is a critical tipping point called the Chandrasekhar limit. If the core is lighter than this, it can stabilize. But if that remnant core is heavier, gravity is so immense that it overwhelms the forces holding atoms apart, and no known force in the universe can stop its complete collapse. It will just keep on shrinking until it forms a singularity, and a black hole is born. For a long time, that was the story. Black holes were the ultimate cosmic prisons. But then came our final chapter. And this part brilliantly shows how a whole new field of physics, quantum mechanics, was about to add an absolutely astonishing twist to the story.
So here's the question that changed everything. Are they truly perfectly black? And once they form, are they really eternal? The classical theory, the Einstein theory, said yes, but quantum mechanics had a very different answer.
In the 1970s, Stephen Hawking was studying the strange physics right at the edge of the event horizon. He decided to combine the two pillars of modern physics, general relativity for gravity and quantum mechanics for the very small, and what he found was revolutionary. It completely upended our picture of black holes. He discovered they actually glow.
He proved that black holes must have a temperature and emit a faint thermal radiation, which we now call Hawking radiation. This process carries energy away, meaning the black hole is slowly losing mass. Over truly unimaginable timescales, trillions upon trillions of years, this slow leak will cause the black hole to completely evaporate until nothing is left. Black holes aren't forever.
And this leads to a fascinating paradox. You might think the biggest black holes are the most powerful, but in this case, it's the opposite. The most massive black holes are actually the coldest, and they evaporate the slowest. It's the tiny, hypothetical micro-black holes that would be incredibly hot and would evaporate away in a brilliant flash of energy.
This leads to an even deeper mystery. This faint glow implies that black holes contain information. But here's the really weird part. The amount of information isn't stored in its 3D volume like you'd expect. Instead, it's proportional to the 2D surface area of its event horizon. It's like all the information for a massive 3D object is somehow written on its 2D outer shell.
Which leaves us with this final, tantalizing question. Black holes are the one place in the universe where our two best theories, general relativity for the very large and quantum mechanics for the very small, are forced to work together. Could a complete understanding of these enigmatic objects finally unlock the single, unified theory of everything that physicists have been searching for? The journey that began with a simple question about a dark star might just end with the answer to it all.